Testing, testing. Materials testing and structural testing. Destructive or non-destructive? The difference is clear-cut. Destructive testing leaves you without a serviceable component or test specimen once the testing is over. The Sharpie test, the bend test, the tensile test, this chassis box section, this pipe section, and this car. They're all destroyed in the testing process. Well, that's no use if your structure is in daily service. So that's where non-destructive testing comes in. In this short introduction to non-destructive testing, we're going to be looking at half a dozen of the most common types of NDT. And also take a glance at a few of the less traditional newcomers to the field. Well, let's get started with magnetic particle inspection. We use MPI, as it's known, to find surface and just beneath the surface discontinuities in ferromagnetic materials. And we do it by introducing a magnetic flux into the material. An ink containing extremely fine ferrous particles is applied to the surface of a ferromagnetic material, whilst a magnetizing field is applied. Flaws cause leakage of magnetic flux, which creates new magnetic poles. So the ferrous ink particles are drawn to the site of the flux leakage field disturbance, and the inspector sees it. There are a couple of types of MPI: color contrast and fluorescent. With color contrast, a very thin layer of white contrast paint is applied. Magnetic force is also applied and black ink sprayed on the surface. We blow the excess away and any defects or discontinuities show up black against white. With the fluorescent technique, we coat the component under inspection with a fluorescent medium while the part is magnetized. Under a fluorescent lamp, discontinuities or defects show up vividly as bright green. It's a more sensitive technique than the color contrast method. Now, liquid penetrant inspection works on non-ferromagnetic materials for locating surface defects only. We clean and degrease the component, then apply a brightly colored penetrant, which in due course is drawn into the surface breaking defects. After a specified period, the excess penetrant is wiped off and a powder developer applied. It works rather like blotting paper, drawing the penetrant out of the flaws so that they stand out in sharp contrast to the surrounding material. After a specified bleed time, the defects are recorded. Now, radiography is an entirely different type of non-destructive testing. X-rays are produced by directing a stream of high-velocity electrons across an evacuated chamber against an angled target material. The X-rays pass through almost every material and can be detected by a sensitive film on the other side. However, a high-density material will absorb X-rays, while low-density materials allow a greater proportion of them to pass through. For radiographic inspection, there's no need for surface preparation before testing. But you do need to have access to both sides of the component. The film, which is highly sensitive to X-rays, is placed on one side, and the X-ray source is carefully located opposite. The X-rays pass through the component and create a latent image on the film on the other side. Any volumetric flaws or discontinuities in the component allow more of the radiation onto the film, and this creates a darker image on the radiograph. In recent years, wet radiography, which uses photographic films and traditional darkroom technology, has been overtaken by digital radiography. Now, digital radiography relies on the ability of certain substances to fluoresce when they are exposed to X radiation. The fluorescence that's emitted from the substance is made to create an analog electronic signal, which can be converted to a digital signal by means of an analog to digital converter. During testing, a fluorescent-coated surface is placed behind the test specimen. As the radiation passes through the specimen, it causes different levels of fluorescence to occur on the coated surface, depending on the dosage received, and this is controlled by the specimen geometry. This is then converted to a digital signal and displayed on a screen. Microfocus test equipment differs from standard radiography kit in that the focal spot size is extremely small, typically in the micron range. The benefit is that it produces radiographs with extremely high definition. The equipment lends itself well to producing large magnification images while retaining good definition of tiny defects. Some of the benefits of digital radiography over wet radiography are obvious. There's no need for chemical processing. The exposure to image viewing time is shorter. The images are easily stored on a hard drive, and they can be easily manipulated and enhanced on a computer. Well, now let's look at ultrasonic testing. UT, as it's known, is actually a generic title for several different methods of generating and observing ultrasonic signals. They're all different, but use the same basic principle. They all use a signal above the audible frequencies, hence the word ultrasonic. This is passed from a probe into the component under investigation. The signal bounces or is reflected when it comes across a discontinuity. If we can measure how long the signal takes to return, knowing the speed at which it travels, we can tell where the discontinuity is. Time of flight diffraction, another type of UT, is used mainly for sizing planar floors orientated perpendicular to the surface. However, it's less reliable when there's a high density of defects, when the material contains scattered inclusions, and also with coarser-grained materials. TOFT is widely used in the petrochemical and nuclear industries for the inspection of butt welds in pressure vessels and process pipework. It's often used to provide critical floor sizing data for input into engineering critical assessments. Phased array systems work quite differently. They offer the possibility of performing inspections with ultrasonic beams of various angles and focal lengths, using a single array of transducers. So, what's it used for? Well, finding the same manufacturing flaws like lack of sidewall fusion, lack of root penetration, lack of root fusion, and porosity, in-service flaws like fatigue cracking, stress corrosion cracking, corrosion and erosion, and parent material flaws like inclusions, and lamellar tearing, only it does it quicker and with a reduced amount of scanning. A specific application of phased arrays lies in pipe girth weld inspection, particularly in installation of long pipelines, where it replaces conventional systems with many probes. This technique is also used for the rapid inspection of thick-section pressure vessel welds, turbine discs, shafts and blade roots, fillet welds, and welds in coarse-grained materials. So now to surface ultrasonics. It tends to be used for the detection of environmental cracking in petrochemical plant, and also fatigue cracks in civil engineering structures like bridges. As the name suggests, surface waves travel along the surface of components, penetrating to a depth of only one ultrasonic wavelength. It's used to find planar flaws that break the surface and lie at 90 degrees to the scanned surface, such as fatigue cracks in weld toes and also stress corrosion cracking. Finally, long-range guided wave ultrasonics make use of low-frequency guided waves to detect corrosion and erosion in pipework. The main advantage of the technique is that it provides 100% initial screening coverage of a long length of pipe and only requires local access to the pipe surface at those points where the transducer array is attached. It's suitable for use on pipe diameters above 50 mm and on wall thicknesses up to 40 mm. It's used specifically to find both internal and external corrosion, and also erosion in thermally insulated coated and buried pipework, corrosion under pipe supports, and hidden welded joints. So it finds its niche in petrochemical process pipework, oil and gas transmission lines, gas manifolds, offshore risers, jetty lines, and power station boiler tubes. Now to eddy current testing. In standard eddy current testing, a circular coil carrying an alternating current is placed close to an electrically conductive specimen. The alternating current generates a changing magnetic field which interacts with the test object and induces eddy currents. Standard eddy current testing is essentially a near-surface technique. It's useful for detecting surface breaking or near-surface cracking and variations in material composition. Eddy current methods are used for surface inspection of both non-ferritic and ferritic materials. Eddy current penetration is deeper on non-ferritic materials, so it's also used for special applications with thin components, such as in the inspection of multiple layer airframe components for cracking or corrosion thinning. Lastly, to thermography. Thermography is the simplest of all thermal inspection techniques. It involves using an infrared camera to look for abnormally hot or cold areas on a component operating under normal conditions. Most modern thermal cameras are able to detect temperature differences of less than 1/4 degree Celsius, and they enable thermal images to be recorded on video or computer disk for future analysis. Thermography is a remote technique for use in most areas of plant, but is particularly suited to equipment operating at elevated temperatures. Active thermography, where heat is applied directly to the component, is used for inspection of low conductivity materials like composites,